multimode optical fiber is a type of optical fiber mostly used for communication over short distances, such as within a building or on a campus. Typical multimode links have data rates of 10 bits to 10 Gbits over link lengths of up to 600 meters more than sufficient for the majority of premises applications. The equipment used for communications over multimode optical fiber is less expensive than that for single-mode optical fiber. Typical transmission speed and distance limits are 100 Mbits for distances up to 2 km, 1 Gbits up to 1000 am, and 10 Gbits up to 550 am. Because of its high capacity and reliability, multimode optical fiber generally is used for backbone applications in buildings. An increasing number of users are taking the benefits of fiber closer to the user by running fiber to the desktop or to the zone. Standards-compliant architectures such as centralized cabling and fiber to the telecom enclosure offer users the ability to leverage the distance capabilities of fiber by centralizing electronics in telecommunications rooms, rather than having active electronics on each floor. Comparison with single-mode fiber. The main difference between multimode and single-mode optical fiber is that the former has much larger core diameter, typically 50–100 micrometers. Much larger than the wavelength of the light carried in it. Because of the large core and also the possibility of large numerical aperture, multimode fiber has higher light gathering capacity than single-mode fiber. In practical terms, the larger core size simplifies connections and also allows the use of lower-cost electronics such as light-emitting diodes and vertical cavity surface-emitting lasers which operate at the 850 nm and 1300 nm wavelength. However, compared to single-mode fibers, the multimode fiber bandwidth or Euro-distance product limit is lower. Because multimode fiber has a larger core size than single-mode fiber, it supports more than one propagation mode. Hence it is limited by modal dispersion, while single-mode is not. The LED light sources sometimes used with multimode fiber produce a range of wavelengths and these each propagate at different speeds. This chromatic dispersion is another limit to the useful length for multimode fiber optic cable. In contrast, the lasers used to drive single-mode fibers produce coherent light of a single wavelength. Due to the modal dispersion, multimode fiber has higher pulse spreading rates than single-mode fiber, limiting multimode fiber unregistered trademark S information transmission capacity. Single-mode fibers are most often used in high-precision scientific research because the allowance of only one propagation mode of the light makes the light easier to focus properly. Jacket color is sometimes used to distinguish multimode cables from single-mode ones. The standard TIA 598C recommends, for civilian applications, the use of a yellow jacket for single-mode fiber, and orange or aqua for multimode fiber, depending on type. Some vendors use violet to distinguish higher performance OM4 communications fiber from other types. Multimode fibers are described by their core and cladding diameters. Thus, 62.5/125 AA micrometer multimode fiber has a core size of 62.5 micrometers and a cladding diameter of 125 AA micrometer. The transition between the core and cladding can be sharp, which is called a step index profile, or a gradual transition, which is called a graded index profile. The two types have different dispersion characteristics and thus different effective propagation distance. Multimode fibers may be constructed with either graded or step index profile. In addition, multimode fibers are described using a system of classification determined by the ISO 11801 standard OM1, OM2, and OM3 which is based on the modal bandwidth of the multimode fiber. OM4 was finalized in August 2009, and was published by the end of 2009 by the TIA. OM4 cable will support 125 m links at 40 and 100 Gbits. The letters OM stand for optical multimode. For many years 62.5/125 AA micrometer and conventional 50/125 AA micrometer multimode fiber were widely deployed in premises applications. These fibers easily support applications ranging from Ethernet to Gigabit Ethernet and, because of their relatively large core size, were ideal for use with LED transmitters. Newer deployments often use laser-optimized 5125 AA micrometer multimode fiber. Fibers that meet this designation provide sufficient bandwidth to support 10 gigabit Ethernet up to 300 meters. Optical fiber manufacturers have greatly refined their manufacturing process since that standard was issued, and cables can be made that support 10 GBE up to 550 meters. Laser-optimized multimode fiber is designed for use with 850 nm VCSELs. The migration to LOMMFOM3 has occurred as users upgrade to higher speed networks. LEDs have a maximum modulation rate of 622 Mbit because they cannot be turned on or fast enough to support higher bandwidth applications. VCSELs are capable of modulation over 10 Gbit and are used in many high-speed networks. Cables can sometimes be distinguished by jacket color, for 62.5/125 AA micrometer and 5125 AA micrometer, orange jackets are recommended, while aqua is recommended for 5125 AA micrometer laser-optimized OM3 and OM4 fiber. VCSEL power profiles, along with variations in fiber uniformity, can cause modal dispersion, which is measured by differential modal delay. Modal dispersion is caused by the different speeds of the individual modes in a light pulse. The net effect causes the light pulse to spread over distance, introducing intersymbol interference. The greater the length, the greater the modal dispersion. To combat modal dispersion, LOMMF is manufactured in a way that eliminates variations in the fiber which could affect the speed that a light pulse can travel. The refractive index profile is enhanced for VCSEL transmission and to prevent pulse spreading. As a result, the fibers maintain signal integrity over longer distances, thereby maximizing the bandwidth. Comparison: encircled flux. The new IEC April 1, 6/1280 standard called encircled flux specifies the injection size, to make sure the core is not overfilled or underfilled. See also, fiber optic communication, graded index fiber, ISO IEC 11801, references, Telecommunications Industry Association. Multimode fiber for enterprise networks. Retrieved June 4, 2008 ABCDEFGHI Furukawa Electric North America. OM4, the next generation of multimode fiber. Retrieved May 16, 2012 ARC Electronics. Fiber optic cable tutorial AB fiber optic cable color codes. Tech topics. The Fiber Optic Association. Retrieved September 17, 2009 Crawford, Dwayne. Who is Erica Violet and what is she doing in my data center? Tech topics. Belden. Retrieved February 12, 2014 British Fiber Optic Industry Association. Optical Fibers Explained. Retrieved April 9, 2011 Fiber Optics Overview. Retrieved November 23, 2012 Meeting Report Number 14. Telecommunications Industry Association Kish, Paul. Next Generation Fiber Arrives. Cabling Networking Systems. Business Information Group OFL Overfilled Launch for 850 nanometer per AM effective modal bandwidth for 1310 nm, ABCDE Hewlett-Packard Development Company, LP100 Base FX Technical Brief. Retrieved November 20, 2012 AB40G Extended Reach with Corning Cable Systems OM3/OM4 connectivity with the Avago 40G QSFP plus ESR4 transceiver. Corning 2013. Retrieved August 14, 2013 Force, Incorporated Types of Optical Fiber. Archived from the original on October 12, 2007. Retrieved April 17, 2008 Hayes, Jim. Karen Hayes. Lenny Lightwave's Guide to Fiber Optics. Retrieved June 4, 2008 International Engineering Consortium. Fiber Optic Technology. Retrieved June 4, 2008 Telecommunications Industry Association. multimode fiber for enterprise networks. Retrieved June 4, 2008. Telecommunications Industry Association. Choosing the right multimode fiber for data communications. Retrieved November 17, 2008. Hewlett-Packard Development Company, LP100 Base FX Technical Brief. Retrieved November 20, 2012.